There we go. And I'll turn things over to group 534M.
All right. Hello and welcome to our presentation, everyone. We are so happy you could join us. We are Team BioReactor, and our product name is Shakeinator 810. Our members are Ami Patel, Armand Pasqua, Lotzi Thompson, Logan Laird, Natalie Lopez, Robert Brunner, and Rudy Oliva. This presentation will cover key product specifications, testing results, unique design features, prototype evolution, and cost analysis. So, for the overview of our shaker table, we're going to introduce the unique advantages enabled by utilizing a CoreXY design. Often seen in FDM printing, the CoreXY concept uses two stepper motors with a neoprene timing belt and rail pulley system to provide precise motion in the X and Y direction of the table. This allows for a shaker that is compact with high control versatility. The design is also ergonomically shaped with ideal symmetry, making it very lightweight and enabling the user to easily transport it. Although our product has been coded for linear, orbital, and double orbital shaking patterns, a unique feature of the design is that any type of shaking pattern can be coded into the user interface if deemed necessary. This makes for a fantastic value proposition. Additionally, low friction ball bearings enable our design to operate with minimal maintenance, and the design is also capable of operating at high speeds without generating excessive amounts of noise. In addition, user-friendly holster clips hold the custom-sized tube rack and standardized well plate firmly in place during shaking. Also, the shaker's mechanical coverings can be easily removed, making cleaning very manageable.
At the beginning of this project, we found that all team members had a good understanding of 3D printer operation from experiences both in and out of school. This shared understanding led to a passion for developing a similar 3D printer-based movement system that combined our experience and knowledge together. This movement system is commonly known as CoreXY and allows for the design to be highly skilled in space utilization and efficiency. The design is compact, but it still allows for a wide range of customizable shaking path speeds and diameters, which drives our economic engine and leads to our overall Hedgehog concept, tiny but mighty. Our design is a 3-rail system that features stationary motor movement in one plane. The CoreXY movement system allows our design to be very compact and lightweight, while still being capable of a customizable movement system with adaptive orbital ranges for linear, orbital, and double orbital motion. This supports different mixtures that could be used for a shaker that require different excitations, as it can move in all needed shaking paths at a variety of speeds and ranges. Additionally, at its size, 2 of our shakers could fit within the designated bioreactor space defined by customer need 1, while supporting both a tube rack and well plate simultaneously. The control box is also placed to reduce unnecessary space as well and provide a sleek design. It reduces low operation noise and contains minimal and easy maintenance features for users too. The customer needs were referenced for all critical components and features for our design and are summarized here in this table. These features are expanded upon further in this presentation, and so as a reference, in the top left of each slide, there will be banners denoting which customer needs are referenced for those features.
So we've used the term CoreXY a few times already, and we thought it'd be kind of important to expand on what that really is for those of you that don't know. So there is a common type of 3D printing known as FDM, stands for Fused Deposition Model. That's like your stereotypical, almost like a glue gun type of 3D printing. It's the kind that when you think of 3D printing, that's what you picture. So in FDM printing, somebody at MIT developed this belting pattern called CoreXY, and it's essentially the belting pattern that you can see in the right side of the screen here, where you have 2 separate stepper motors. Each has their own belt and pulley system, where when one motor is actuating, it actually controls it in the 45-degree instead of directly in those X and Y axes as you would normally expect. The positive of this is that it allows you to get high precision without needing to stack motors on top of each other. And so that's what really allows us to get that small but mighty situation that we've got. So to kind of break it down using the diagram, if you were to take the purple stepper motor and actuate it counterclockwise, you would get motion in this 45-degree angle. Alternatively, if you were to take the orange stepper motor and actuate that counterclockwise, you would get that 45-degree motion. So you can kind of see it's really just the X and Y, but shifted negative 45 degrees. So then at this point, it's really just a sum of vectors, right? If you want to go in one direction, it's just going to be a combination of those at combinations of speeds. So if we assume for a second that we're only working at the same speed and we move both motors counterclockwise, what you're going to get is a positive Y direction of movement. Whereas if you move them in different directions, you're going to get an X motion. And basically just using that fundamental concept allows you to get as many different shapes that you want. So on top of just like CoreXY itself, we also had a unique coding solution on how to make this work. Essentially, we took all three path patterns defined by the user, which was orbital, which is just a circle, double orbital, which is 2 circles, so a figure 8, and then linear, which is just a line, right? We basically took, let's figure out how to do a circle and then use that to define the other methods. So starting with the circle, it's not so easy that you can just tell your table in your code, go in a circle. Like it doesn't work that way. You need to tell your motors how many steps to do at what speeds. So the way that we approached this is we defined the circle as 16 points around it. So essentially you can break down a circle into segments of pi/8, and then using the unit circle, you can define scalable values that are then multiplied by the diameters and accounted for the other user inputs that will be taken later. And you essentially get this matrix of a circle. To get the linear pattern, what we did is we just turned one motor off. So it still did that circular motion where it would speed up in the middle and slow down at the ends, making a more fluid motion as opposed to a jarring here, here type thing. And then for the double orbital, what we did is we just divided the diameter of the user by 2 and then made a circle the same way that we did before. And then when it completed that first circle, we made it do a negative circle back. And then you just repeat that. And that's how we were able to use CoreXY with our code.
Thank you, Lutzi. And so moving into the design specifications of our design, the first feature I'm going to note is the simple tube rack and well plate mounting. This ensured that one could easily access and detach the well plates and tube racks without interfering with other parts of our design. Next on the right, you see the enclosure we designed, and this was done in order to protect the system's interior as well as provide a sleek design. We wanted to make sure that the enclosure could be easily detachable in order to make assembly and maintenance processes easier. Then on the bottom right, you see the mechanical safety stops that we made, and these are located at the idler rail blocks and motor mounts in order to increase safety and prevent projectiles. There's also some limit switch electrical stops that enhance the safety of our system too. And so the different subsystems of our design, if you look at the left, you see the user interface, which houses all the electrical components and allows a friendly user interface for the user. And then on the right, you see the shaker plate subassembly, which attaches to the rail subassembly through 4 fasteners. And then the rail subassembly loads onto the base subassembly's rails.
Thank you, Natalie. So basically now I'm just going to talk about each of the individual subsystems that she outlined. So first up, we have the base subassembly. In this subassembly, it features 2 NEMA 17 stepper motors to accurately control the belt drive system, a parallel set of rails for the Y-axis motion, an integrated control box, a limit switch that both locates the shaker table in the Y-axis and acts as a safety stop if the shaker moves in an unintended direction. Idler mounts with simple yet highly effective tensioning slots to ease the installation of the belt system, and rubber feet to prevent sliding under high frequency use. In addition to the limit switch safety stops, the base subsystem also incorporates hard mechanical stops to ensure the shaker plate can never become a hazardous projectile. The structural components of the shaker table were designed to be manufactured out of 6061 aluminum, so that the whole device as a whole is sturdy and does not flex, allowing the bottom rails to remain parallel to one another. Next up, we have the rail subassembly, and this subassembly features 3 rail blocks with integrated ball bearing sliders for smooth, near frictionless motion. The idler mounts serve to properly align the 4 pulleys at distinct levels to keep the belt drive system taut, while also routing the belts around internal components such that there is no interference with other parts of the design. The belt tie-down system is composed of 3 parts that clamp the ends of the belts to the center rail block. These parts are ridged such that there is positive mechanical engagement on the belts, ensuring it does not slip and become loose over time. The subsystem also includes a limit safety switch as a safety stop for the X-axis and hard mechanical stops in both directions. Finally, we have the shaker plate subassembly. So seen here is one of the key features of this design. That is the ability to shake both a well plate and a conical tube rack at the same time. It helps increase the volume of testing that you can do at any given point. The conical tube rack shown is a custom-made 3D printed part that maximizes the amount of conical tubes that can be packed in for a given area. Securing the well plate and tube rack to the shaker plate is a simple yet effective system of clips. Securement method for the tube rack and well plate was designed with ease of use in mind, such that a simple snap in or snap out allows for the change of well plates or tube racks on the shaker plate in a matter of seconds. In addition to the clips, tube rack and well plate are secured tightly to the shaker plate using what we call a well wall. Using this well wall is what allows the tube rack and the well plate to come in and out of the shaker assembly so easily, while still being held tightly under normal operation. The clear acrylic shaker plate also allows for easy support and integration of an ODFI system, as shown by the representative model.
Thanks, Rudy, and good morning, everybody. This is our user interface, and our user interface allows the user to have complete control over the path, speed, size of that the shaker table follows. This is done through the 3 dials I can see on the bottom. From left to right, you have the speed dial, which has 5 different settings ranging from 0 to 350 RPM. The pattern dial in the middle, which allows linear, orbital, and double orbital, and the size, which allows adjustment, 5 different settings, all the way up to 25 millimeters. This satisfies customer need 20, which requires at least 2 user inputs to control these factors. Other than that, we have a fail-safe stop button that you can see on the right that allows you to pause the motion of the shaker table without completely turning off power. This allows you to keep the timer stopped as you make any changes, switching out liquids or switching out test tubes. On the left, you can see the timer reset button, which when paused allows you to set the timer back to 0. And in the middle, you can see the LCD screen, which displays all the information you require. This is the LCD screen before it starts running, so there's no timer on there, but you can see the RPM, diameter, and pattern shape that the shake table will run at. This is the user interface from the back. You can see our hard emergency shutoff function as our power button on the right side of the shaker table. Furthermore, all our electronics are stored in the shaker table. This allows us to do a few things. One, it allows easy access to electronics to replace any components that might be damaged, as well as quick disassembly because all the electronics are on a tray. Furthermore, since the user interface would be outside of the bioreactor, it allows the electronics to not be in danger by any of the heat within the bioreactor from any chemical reactions or anything like that. Also, to cool down all the electronics, we have 2 fans that bring in cold air from the environment and transfer it over the electronics and push that through the vents on the other side. You can go to the next slide. Here you can see a diagram of the heat transfer, and this worked really well, and we'll go into it in further depth later, but we were running the risk of our motor drivers overheating because we were putting so much power through them. So this system of fans, along with the heat sinks on the motor drivers, completely prevented any of those issues that we were encountering and allowed our system to run for up to 2 hours with no problems whatsoever.
So next up, we have a walkthrough of the UI from the perspective of the user. So first, the user will turn on the UI, and as it loads up, it's going to say BioReactor Model 810 Proto, as in prototype. Then you have your different shape options that they can go through. So you have orbital, double orbital, and linear. Then the RPMs can also change, reminding that they are 5 different options, and the same goes with diameter. So once a selection is made, the user then puts it onto start, and the shaker table will then start to center. Now let's say you've been running the same culture for a while, and it's time to swap them out. So basically, the user would pause the table and then take it out easily with our, in and out clips, and then they'd want to reset the timer because it's a new culture. So you simply hit the timer reset and it goes back to 0. Then begin again, and there it goes. Then to turn it off, you would simply hit the stop button or turn it off on the power button on the right.
Thank you, Lotzi. Over time, our team developed and improved our design repeatedly to improve its function, meet customer needs, and develop the amazing prototype that we've been presenting to you all. The overarching goal of our team was to develop a tiny but mighty shaker table. So we reduced the size of our base plate and tabletop to make a more compact design that's easy for users to carry and transport when necessary. Additionally, it was vital for our design to have a sturdy and level base plate. When working with timing belts and pulleys, proper alignment is critical, and an uneven base plate could disrupt the entire function of the table. So to make our base plate even more steady, we featured 6 rubber feet at the bottom of it, 4 on the corners and 2 around the middle. This keeps the table level, prevents sliding, and reduces the noise level when the shaker table is running. To ensure that the rail blocks have no chance of sliding off the rails and that the design is safe for our users, we featured 2 limit switches on the rails, one in the X direction and another in the Y direction. Additionally, it is important for the timing belts to be tight. However, because it is possible that they loosen over time, we developed an easy-to-use tightening system consisting of idler mounts and slotted idler screws, as shown earlier. This way, the customer can adjust the tightness themselves as needed very easily. Lastly, we developed a holster clip and plastic holding rail to keep the well wall and tube racks firmly in place. Essentially, the well plate and tube racks are tightly secured by a wall on one side, and on the remaining 3 sides, they have holster clips keeping them in place. This also makes it very easy for the user to snap in and out their well plates and tube racks. To determine the cost of a prototype of our design, our team calculated the sum of OTS parts, raw material, manufacturing costs, and assembly costs for the device. The OTS cost for a prototype totals to $821.30, consisting of 37 parts, including fasteners, electrical components, pulleys, rails, and more. The cost of raw materials sums to $94.99 for a prototype, and this consists of aluminum bars, rods, acrylic sheets, and sheet metal, which were used to manufacture products such as our base plate, tabletop, the enclosure, and more. The cost of manufacturing these components was calculated considering their part geometries, as well as the manufacturing processes that would need to be applied to each part to produce our final project, such as drilling and tapping holes, machining, and 3D printing. To determine the assembly cost, our team timed ourselves fully assembling our shaker table, and it took just under 2 hours. Assuming we pay the worker $16 an hour, this amounts to $32 for assembly cost. In total, this summed to a prototype cost of $1,082.49. Now, for a 100-unit mass production run of our design, the same approach was taken to determine the cost. The total cost per unit ended up being cheaper than the cost of developing a prototype, considering buying items in bulk, such as fasteners or electrical components, is much cheaper than buying an individual unit. For a 100-unit mass production run, the cost per unit totaled to $832.76. For reference, a thermoscientific microplate shaker table costs $1,235 a piece, And these shaker tables are not capable of producing complex patterns such as a double orbital, like the Shakenator 810.
So now we're going to talk about a little bit of our analyses that prove to us our design would work before constructing it in real life. So customer need 8 required that our factor of safety for all structural components was at least 1.15. We went above and beyond that and found a factor of safety of at least 1.5 for all critical features. One of the first things we did was did a 3-point bending analysis on the center rail that supports the shaker table via the one rail block. We assumed the worst case scenario for this would be if the rail block were placed directly in the middle and a 5-pound load were applied. This 5-pound load was found by measuring the weight of all the components that rest on top of the rail block, less than a pound, and then assuming you might have 4 pounds or more of liquid just to get a nice round number. After doing this bending analysis, we found that the maximum bending stress was 1 megapascal, and the yield stress is 215 megapascals. So we had a factor of safety much greater than 1.5. For the motor shaft bending, due to the torque from the belts, we did a bending analysis here. And for this load, we used 32.3 pounds, as this was the maximum working load for the neoprene belts. We found that under this load, there was a maximum bending stress of 160.6 megapascals, which provides a factor of safety of 1.6. Lastly, we determined how well the acrylic shaker tabletop would function. We did this by assuming that the center of the shaker tabletop was a fixed point and applying a point load all the way to the end and treating it as a beam. We applied a load of 2.5 pounds, half of what we used for our 3-point bending, since this is half the shaker table. And we found a maximum deflection of less than 0.35 millimeters, which is within the elastic range and would not cause any damage to the shaker tabletop.
Thanks, Armand. Our analysis was conducted on the key electrical components in our design to ensure that there was not risk of thermal failure. First, the power supply was validated to be able to power the entire system. Our design uses a 24-volt DC 5-amp power supply, which can supply up to 120 watts for the entire system. The power drawn from the motors, Arduino, and motor drivers were found from their operating current and voltage specified by the manufacturer. The overall power input to the entire system was found to be 99.7 watts, which is within the power supply's capabilities. The temperature rise for each component was then determined under worst case scenario conditions of 70 degrees C ambient conditions. For each component, the power they drew from the system was compared against the component's efficiency. This was used to determine the amount of power that is dissipated as heat in each one, contributing to a temperature rise. When necessary, conservative estimates were made to model each system under its highest possible load. One such estimate was modeling the entire system under natural convection conditions, without the fan running, to understand how the components would perform. The temperature rises were then compared against the component's maximum allowable junction temperatures specified by the manufacturer, and the risk of thermal failure was determined. Under these conditions, all components had appropriate safety margins from their maximum allowable temperatures, with the exception of the motor drivers. This component had a risk of thermal failure under high load conditions and could also experience decreased performance with normal operation. This drove our decision to include a fan in the UI to cool these components. This decision was validated with performance testing, which showed that fan inclusion greatly increased thermal and machine performance.
For our endurance tests, we ran the 3 different shaking patterns for extended periods at 350 RPM. The orbital test was run for 2 hours, while the double orbital and linear tests were run for 55 minutes each. There were no thermal or structural failures recorded during testing. Furthermore, we expect that the shaker will be able to run for 2 weeks without any issues. Thanks for coming, everyone. We really are glad that you could see our presentation, and we really hope you enjoyed it. And so now we can move on to questions from the audience.
Okay, questions from our panelists.
I can go first. Hey, Great job, team. I haven't been to any of these presentations yet. I thought you guys did a wonderful job. You did a fantastic job off the bat, kind of explaining the requirements, going into like your CoreXY movement, explaining FDM. I thought you guys did a great job explaining a lot of things, going into even like the coding movement. And when it got to the BOM, I really like seeing kind of how everything comes together. So seeing that visual helped me a lot to understand what it is you guys have been working on and putting together. So just great job there, just a lot of positivity. One question I do have, and kind of we started to get into it on slide 12 when we were kind of seeing the small rubber feet on the bottom of this, and then on slide 24, we got to see this actually kind of oscillating and in work. One question I do have is, do we have any concerns of this thing kind of walking on a table? It kind of seemed like it was starting to maybe move on the table, and I noticed we were testing this without any kind of items on the plate. I don't know what the intent is on what the fully loaded capacity is, but once we get all that weight on there, do we see an issue with it kind of walking since we've added that much more mass to the kind of moving parts? So that's kind of the only question I have.
Yeah.
Michael, yeah, I'll take it.
I can take it.
Okay, cool.
So it did walk when we were doing the endurance testing. That was an issue we had, but we believe the reason is because our base plate in this model is 3D printed, so it's really light and doesn't give you that like mass to hold it down. Whereas in our, theoretically, it would be made of aluminum in the future.
Yeah, that's a good point. I mean, aluminum's still going to be relatively lightweight. It's going to be kind of a balancing act to figure out how much weight you have on kind of the shaker portion. Just if you need to, I mean, you can possibly even make it out of steel or whatever it takes to just increase that overall bottom mass of your assembly. That way, kind of the part on top isn't causing the base to walk around. And if you have to, maybe you could find a way to fasten it to a table. But that's just one thing I noticed when to put it out there. But overall, I thought you guys did an excellent job. So great work, everyone.
Thank you.
Thank you.
So yeah, guys, I want to echo the comment on a great presentation. You guys did you probably weren't expecting me to say that. But yeah, you guys did a great presentation. Can you go back to your cost slide real quick for me?
Which slide?
Cost.
Yes.
Yeah.
Oh, wait.
Yeah. Who am I? What have I done with? I murdered him and left him in a closet. So yeah, so your costs right now are overwhelmingly OTS parts. That's to be expected, kind of how we run the class and our limitations on how much time you would have to manufacture things. It definitely does shift over to what I like to call death by McMaster car. Moderately necessary evil. But if you were to go and take a look at all of your OTS parts, what parts could you end up manufacturing to transition some of that where you would be able to make them cheaper than you can buy them OTS if we were to make them in-house?
I think
That's a great question. Oh,
no, go
Lucy,
for
There's
it.
definitely a lot
Okay.
of parts you can.
there are many parts that we could definitely manufacture ourselves. I think for the purposes of this class, obviously we opted for purchasing a lot of them just to make the process more streamlined and ensure that we got the stuff in time. But definitely a lot of our rails could be manufactured. Those are straight up just blocks of metal with different manufacturing processes applied to get the right holes in place. Those could definitely be manufactured. Obviously, we would still want to purchase other electrical components, which is a lot of those 37 OTS parts, as well as the fasteners. But definitely the rails. We also purchased rubber feet, and we had spacers for the rubber feet as well. Those rubber feet could the spacers could definitely be manufactured. Yeah, just I think maybe our pulleys as well, because those are also just solid blocks of metal.
Yeah, I would say the motor mounts would have been the first thing to manufacture, because I don't know, it's really just metal with holes in it.
Definitely the control blocks as well. It's just a box made of plastic.
Yeah.
So
All right, cool. That was
Hey.
my question.
What's up, Alex?
Hey, how are y'all? I just want to again echo the same point everyone's been making in that I think this was definitely one of the most confident presentations so far. I mean, everything was very, very smooth. It just sounded very well prepared and very confident. So I just want to say good job, guys.
Thanks, Alex.
Thank you, Alex.
I also wanted to echo really, really great, outstanding, smooth, slick presentation. Easy for the non-mechanically inclined people such as myself to follow, which I appreciate. I just had one minor comment, which is with the UI, you have the stop, the soft stop kind of button, but it's also the start button.
Yeah.
And I think it'd be useful to, in addition to having stop, have start maybe above it so that it's clear to the user that, oh, this is on off kind of thing.
Yeah. That was always in the works. When we initially just had a button there, and then I made a last minute decision to change it from a button to a rocker. And I was like, well, I'm not going to 3D print this again.
Yeah.
So I literally
well,
took a hand drill and like increased the hole of the buttonhole and like added in the rocker switch. And I was like, we're just going to put a sticker there, but then we ran out of time. So.
Well, I think that the rocker is definitely a good choice. But yeah, just when I first saw the image, I could not tell from the image that it was a rocker, and I was wondering, how do you start this thing?
Yeah.
Until saw the video. Oh, okay. So, but great presentation. I really enjoyed it. Thank you.
Thank you.
I suppose the rocker switch also aligns with the team name.
Of course it does. That was intentional.
Everything was planned.
Okay, any other questions, comments from our panelists?
I'll go and add another comment that I think I don't know how many teams have done. I think you guys are like the second team that's shown a heat transfer analysis or any sort of like actual math on or looking at the thermal concerns. So, you know, just I mean, there was one group that talked about thermo yesterday, I think, and then you guys today with having done a heat transfer analysis. I know that thermal effects were a huge thing for a lot of groups in the class, and I appreciate you guys actually acknowledging that concern and showing the math instead of just the, yeah, we did this thing and then we swapped out to this other component because the first one melted. It's like, well, it's like, yeah, well, you figured out why the problem existed, not just that it was a problem and this fixed it. So thanks for being engineers is I guess what it really boils down to.
Additionally, more on that, I think this was the only team out of all of the teams, correct me if I'm wrong, that actually did not only attempt and succeed in implementing some sort of active cooling with a small fan across their drivers.
Yeah, thanks. The fans really made a world of difference because we were experiencing skipping because the drivers got so hot that the thermal paste became less pasty and the fans started like sliding around as the shaker table moved. But once we had the fans in there, it just, nothing was even close to getting hot. It was perfect. So
yeah, and there were groups, or a lot of groups that did not account for any of the thermal effects. So when they went to testing, actually had to set up an external fan to blow at their motors and their drivers, but none of them actually had the foresight and wherewithal to include it as part of their design. So I just want to say good job again for being engineers.
Thank you. And on top of that, you know, we have 2 fans, one for each driver. So when we like installed the fans and then we made the tray, I was like, we need the motor drivers like the closest to the fan as possible because they were like the most worst case.
I guess I have one question now, looking at the orientation. Your vents for hot air, it appears that the output for them is in the downward, like the air would be coming out and going down.
Mhm.
What does hot air like to do?
Rise.
Precisely. So why have them oriented downward instead of upwards to facilitate with natural convection?
We did that because it was kind of to protect some of the electrical components from outside elements like dust or anything like that. But actually, we included in our improvement plan in the FDR to actually enclose the UI more so that the vents don't have to be oriented down. Could you actually go to the last slide, Lotzi?
To that comment though, I mean, you're still gonna suck it in where the fans are with the dust. So unless you have a filter, I'm not sure what.
Yeah, this is what I mean. So kind of create a little chassis that the electrical components can go into, and then kind of just a little heat sink inside there that encloses all the electrical components, and then just has fins that the airs actually go across. So the electrical components are all protected, but they still get the effects of the fan.
Okay.
So this is just like a quick representation that we included in our improvement plan.
I guess follow up then on my question, where could you put the vents to similarly prevent or help with prevention of outside elements coming in that would allow for the hot air to rise?
On the top?
That's what I was thinking. On like the top edge, with the cover coming out off to the side, so it's able to get up and out, but you're not trying to redirect air that wants to go up because it's hot and redirect it downwards where it's just going to go back up again. Get it so it's flowing in a more natural direction.
Yeah, that makes sense.
A follow-up comment while we're on the kind of vent discussion. I noticed you have a kind of a push button where those fans are. I'm sure they wouldn't hurt terribly bad, but then if you're going to put stuff in there, you can put a wide or something so someone doesn't jam their finger into the fans if they're just reaching on the side of it.
I actually did that multiple times, but the fans are so small that it doesn't actually do any. Like you can't fit a finger in there, so it would just like tickle when I would go to hit the power button. I'd be like, oh.
Well, it can't fit a Lotzi finger in there, but it might be able to fit. You know, somebody might have a pencil in their hand that they're going to hit the button with in a hurry, and then you jam a pencil through it.
Yeah.
So Alex didn't ask my question, and oh yeah, he was about to. I saw him on mute there. Alex.
No, I was actually going to say that this is a very real problem. Oh, sorry, Alexa, stop. This is a very real problem when I was working on old MakerBot 3D printers, where in that fan assembly in the front, there's a bunch of long M3 screws or whatever. And when I was, less mechanically inclined freshman year, I was trying to unscrew these screws out of this fan and kept sticking the Allen key into the fan, and I've broken multiple fan blades doing this. So it is something to think about, but I can ask your question, Dr. Traum, if you'd like me to.
Yeah, go ahead. I mean, we would have asked the same question anyway, so go ahead.
Sure. Okay, so the big question that we're asking all of the groups, and it should be noted that this is not a trick question, this is a genuine question for you to think about and decide. After going through the design, prototyping, and manufacturing phase, and actually seeing this product develop in real life, as well as looking around the room of other students' designs and seeing how some of those other designs actually operated in the physical world, do you believe that this design is in fact the most optimal design to meet and successfully be able to accomplish all of the customer needs? Or if you were to do this project again, if there's a different design that you think you would settle with?
I definitely think it's up there for one of the most optimal of the options I've seen in class. I mean, when we did the lab live demo, before we even had like a truly functioning UI, it seemed like we were getting much more precise motion than everybody else. And we were the quietest table in the room. Like everybody else's was really loud. And I thought, you know, that may not have been a customer need, but it is important. You know, you're running this thing for 2 weeks at a time. You don't want to lose your hearing. And I think for those reasons, we're definitely up there. However, the other CoreXY team did beat us on sound, so they can take that cake. But
Yeah, I think we do nothing but try to improve the CoreXY. I mean, I can't imagine trying a different method for the shaker table. It's
I
definitely
think this, I'm sorry.
the best route to go. Yeah, Logan, you can.
I think another good thing is like ours, just like the size of ours. Ours is like if you see it in person compared to the other shaker tables, it is really small. You know, so it's very compact and everything, which I think is a very good benefit of it.
yeah, there's
Also,
definitely
there are
situations. Oh, you go.
I was just gonna say, our shaker table, I would say from what I've seen, meets most of the customer needs. There are other groups. I remember one in particular had a really quiet table, but I remember it was very difficult for them to switch between orbital, linear, and double orbital patterns. I believe ours is very easy to use, and with our improvement plan and what we would like to change versus what we had intended for the table to be versus what we actually got to do with time constraints, I think our design has the potential to be the best of the group.
So we've officially hit the end of time, but I want to ask one more question since I'm incapable of ending one of these sessions on time. So you guys have touched on this a bunch of times. So you'll remember that day in the lab when you came to me with your kind of initial version or lack thereof of a Hedgehog concept. And I think you guys were like really struggling, as I think most of our capstone students do, with like how to come up with a Hedgehog concept and why you even needed one, right? Like, what is this stupid thing that trauma is making us do, right? So, and we talked about it and sort of fought through it and iterated on it a little bit and finally converged to, you guys have said it a couple times, this idea of tiny but mighty. And I've detected, you know, more than once, that's now kind of a point of, you know, both pride and a feature, right? I've heard you say a bunch of times, we're smaller than everybody else. So can you comment on how having a Hedgehog concept from relatively early in the process, like influenced the overall design thinking and design process for you guys? Like, was that helpful or was it just, you know, this silly thing that Tron made us do?
I'd say it was helpful, like because we started our first, when we did the House of Quality in Milestone 1, the first thing that we saw that we really liked was the spring like independent study. It just seemed like the most like finished one out of the other options, and one thing we really liked was how compact that was too. But we saw some issues with it, like the motors were off to the side, there was some wasted space there. So one of like the first meetings we had was kind of like, oh, we like this design, but we know we can make it better by making it more sleek and taking these other things in. But when looking to do that, we kind of talked about what we were good at and our experiences. I think Lotzi has worked at a 3D printer company. We've all used 3D printers in either research or extracurricular clubs and campus. So we were kind of like, oh, we're all really good at this. We really like this. And we now have a system that can make something that we like before, the spring independent study concept, and just make it smaller and make it better. So that kind of drove our decision, is our past experiences with 3D printing, and then knowing that we liked the concept, but knowing how to make it better. And that kind of drove the entire Hedgehog concept and then drove our entire project.
Yeah, I think the Hedgehog concept really helped us focus more than anything, really narrowed down like what we needed to look at, what we needed to focus on, because there's so many different things you can make more efficient, more versatile. But if we had those little things that we could focus on, you know, it being compact, you know, it being able to operate like a 3D printer, or at least a high quality one, then, you know, that really helped, I think.
And something
Different
else I think is
designs.
worth talking about is that in our first design report, CoreXY did not win the decision matrix. But we had a bunch of different options, and the one that won was actually a rack and pinion. And, we did the thing and we said, okay, we can either do that, or we can go with a design choice that we knew technically lost, but we think has the capability of being something that we can all really like work on and be passionate about. And so that's kind of like what made us change, was the fact that we kind of all agreed this is going to be something cool and something unique and something that we can all get behind, whereas anybody can do a rack and pinion. So that's kind of what the turning point for us was, I think, is when we decided to do that.
Awesome. Okay, thank you. All right. Any final questions from panelists? Nope. Okay, then I guess we'll end it there. So I want to just thank you guys one more time for sharing your design with us this morning, and all the hard work that you guys put in this semester to take this thing from literally an idea on a piece of paper to a functional pre-commercial product. Hopefully you guys got something out of the class that you could take with you into your careers and lives as grad students and so forth as you move forward. But just want to say that we really appreciate the time and effort and creativity and energy that you guys put into the class. It makes it worth it for us as instructors when we see students as passionate as you guys working on these hard intentionally making the problem harder for yourself, and then working through those hard problems and coming to viable conclusions and solutions. So thank you.
Yeah, you guys did a great job. Way to kick ass. Congratulations.
Thanks, guys.
Thank you.
Thank you. Also,
Thank you so much.
Thank you for the support, Dr. Trom, Dr. Nemi, and Alex. We really couldn't have done it without you guys.
For real.
Yeah.
You could have. It just would have hurt a little bit more.
Would have hurt a lot
But
more.
in different ways. But
Yeah.
Congrats, guys.
Thank
you.
you.
If you happen to be one of the ones graduating this semester, double congratulations.
Thank you.
Thanks.
All right, well, let's wrap it up there. I'll hit the record stop button.